All right, so the last part of 2.1 we're going to take a look at has two formulas in it. One formula is for finding what we call the length of an arc. So like if you had a circle and you want to measure how far it is from like there to there, that's the length of an arc. Okay. The other formula we're going to look at is what's called the area of a sector. A sector kind of looks like a piece of pizza. It's got two sides that are straight, and the third side at the top is curved. So it's not quite like a triangle because all the sides aren't straight. But there is a formula we can use to find the area of that shape. So that's the two things we'll take a look at. Both of the formulas that we use today are going to be in radians. So if we have a problem where they give us an angle in degrees, the first step is to change it to radians. All right, so this is 2.1 part 2. All right, so I'm going to start out by looking at this diagram. What I've drawn inside that circle is two different angles. Each angle has been labeled with the Greek letter theta, but they're different size angles, so I can't use theta twice. I've got to use different angle names. So I use theta and theta 1. Okay. R is the distance from the center to the edge. And what do you think the R stands for there?
Radius.
Yep, it stands for radius. And S, that's an S, is the length of the arc in red. So each angle has the same vertex, comes out from the center, hits the circle here and here. This angle hits the circle here and there. And what I'm drawing is an arc between those two dots. And our goal is to figure out a formula for arc length, for S. So let's start with a couple pictures. Let's look at this and make another copy of it. And inside this first angle, or inside this first circle, I'm going to draw an angle. And I'm going to draw an angle that's 90 degrees. Best I can by hand. So it's a 90-degree angle. And now I'm going to draw the arc for where the two rays of the 90-degree angle hit the edge of the circle. So that's from here to there. When I draw a 90-degree angle, and then I draw that arc in red, how much of the perimeter of the circle does the arc in red take up?
Quarter.
Yeah, it takes up a quarter of it. So we have, with a 90-degree angle, the arc is basically a quarter circle. All right. Now, I'm going to double the size of the angle, and I'm going to draw it again. So if I double 90, I get an angle that's how much? 180. For a 180-degree angle, the initial side will still be right there, but the terminal side is going to be rotated 90 more degrees than it was here, so it's going to look like a straight line. And here's my arc. Okay. How much of the perimeter of the circle does the arc take up now? Yep, it takes up half. So the arc is a half circle. So I want to see if there's a connection between what happened to the angle and what happened to the arc. To get from 90 to 180, what did I do to 90?
Multiply.
Yeah, I multiplied it by 2. So I doubled the size of the angle. What happened to the size of the arc?
Got bigger.
Can you be more specific?
180 angle is bigger than 90.
Okay, that's true. It is bigger, but I'm looking for something more precise.
Double in size.
It doubled, yeah. So when I doubled the size of the angle that I drew in the circle, it also doubled the size of the arc. So there's a direct connection between the size of the angle and the size of the arc. Okay? It's called proportional. It means as you change one, the other one changes exactly the same way. So we double the size of the angle, we double the size of the arc. What do you think would happen if I made the angle half as big? What would happen to the arc? It would get half as big. Yep. So however you change one, the other one changes exactly the same with it. Any questions on that? All right. Because changing the angle changes the arc exactly the same way, that makes them proportional, and we can set up what's called a proportion. Now, in order to set up a proportion, you have to write down 4 things. You have a fraction on the left, fraction on the right, and each fraction has a top and a bottom. The 4 things that we're going to fill into our proportion, because angles and arcs are proportional, are these 4 things that I just circled. We've got an angle and an arc, another angle, and another arc. Now, when we set up a proportion, you can set it up lots of different ways. You just have to be consistent. However you do it on the left, we've got to do it the same way on the right. So anybody have a guess at what I could fill in on this side using 2 out of 4 of the things I circled?
Would you call that negative sign thing?
This one?
Yeah.
Theta.
That on the top, that's on the bottom.
Okay, yeah. So theta on the top, S on the bottom.
And then reverse it for the outside.
All right, so what would you put on the other side? And just make sure you set it up exactly the same way you did on the left side.
Theta on top and the S on the bottom.
So say it one more time.
The theta on the top and the S on the bottom.
So we have theta on the top and S on the bottom here. So these are done.
Theta 1 on the top and S2, S1 on the bottom.
Yeah, so theta 1 on the top and S1 on the bottom. Okay, all we're really doing here is, like, if I drew this circle and I said to you that with a 90-degree angle, this arc was 4 inches. Okay. This is a 180-degree angle. How big is that arc over there?
8 inches.
Well, we know it's 8 inches because it doubled, but let's say we didn't know it was 8. We're basically just setting up a proportion. A 90-degree angle gives you 4 inches. A 180-degree angle gives you how many inches? We know this already. How do you know that? Well, I just said to you, 90 degrees is 4 inches. Okay, so that side is known. This side is not known. But because they are proportional, if I cross multiply, I can solve for x, and yes, it would come out to 8 inches. Right? But what the advantage of the proportion is, now if I said to you, okay, let's say that 90 degrees gives you 4 inches, how much would 160 degrees give you? It's a little harder to think about in your head, but it's not any harder to solve as a proportion. You just put a different angle here, and then you're going to solve for that. Right? So you're still going to cross multiply. Okay. So this would be a little smaller than 8 inches, maybe 6 or 7 inches. So that's basically what we just set up right here, except we don't know any of the values. Okay? And that's part of the problem. This proportion is correct, but right now it's not useful because you don't have any numbers in it at all. So if I wanted to set up a proportion to say convert between feet and inches, if I give that to somebody just the way it is right now, is that useful? No. They don't have anything to go off of. There's no numbers in it at all. That's exactly what we have right there. No numbers. What we have to do is fill in one side with a fact that we know is true. What's for feet and inches? What is a fact that's true?
12.
Yeah, 1 foot is 12 inches. Now you've got a piece of information there that you can use to figure out whatever you want. Let's say you want to know how many inches in 38 feet. This will help you figure it out. You just cross multiply and you'll get your answer. But how do you get that? How do you know in 1 foot there's 12 inches? Well, that would just, for us, that would be something we have to memorize, right? It's a definition. We've got to figure out something we can fill in on that side. Okay, theta 1 over S1. And the fact that we can fill in there is something we talked about on Tuesday. So that's why I kind of like to do this one back to back, because it's harder to remember a couple days ago. But we did talk about something on Tuesday. If you have a circle and you draw an angle that's just the right size, there's a couple measurements in that picture that will come out exactly the same. Does anybody remember how big this angle has to be right here to make two of the measurements the same? So again, it's the first thing we talked about when we converted between radians and degrees before we got into the conversions.
45?
No, it's a number in radians.
Oh.
It's a number in radians. What? Yes. If this is 1 radian, then what two measurements there come out exactly the same? And this is what's going to help us fill in something on this side.
The radius and the arc.
Yes. The radius and the arc come out exactly the same if that is 1 radian. Okay? We're going to use that fact to fill in this right-hand side. This is going to be like our 1 foot equals 12 inches. Right? So let's suppose that theta 1 is 1 radian. And if you're like, well, how can you just suppose it's 1 radian? Well, how can you just suppose that 1 foot equals 12 inches? It's what it is. If theta 1 is 1 radian, then it automatically makes this and this equal. So let's write that down. If theta 1 equals 1 radian, then this and that would come out the same. And that's going to be the key right there. The length of the arc will automatically be equal to the radius of the circle. Right, so let's fill that in. On the left side, we don't have anything to fill in there. We're going to leave that as theta over s. But on the right side, we're going to fill in a 1 for theta 1. And we know that if the angle is 1 radian, then the size of the arc is automatically the radius. And they'll give you the radius in the problem. So the radius will be a number. So this entire side will be numbers when you do a problem. Just like this side is all numbers. Same idea. Right. And now I mentioned it a couple times, but when you have a proportion, what kind of multiplication do you use to solve it? Yep, cross multiply. So s times 1, that's just s. And then r times theta. That is the arc length formula. I'll just put it over here. So in order to find the length of an arc in a circle, you need to know 2 things. 1, how big is the circle? What's the radius? And 2, how big of an angle did you draw inside the circle? So that's your arc. That's your radius. And that's your angle. Now, we do have to be careful with the angle because there is something we assumed about it when we made this entire proportion. Just like in this proportion, we made some assumptions. We assumed that you want to work with feet and inches. If you want to work with centimeters, that's not the proportion to use. It doesn't have centimeters in it. What unit did we assume about our angle?
Radians.
Radians, right? I didn't put RAD. Again, we have to get used to not seeing it. It's there. But we suppose that theta 1 was 1 radian. That's the unit we assumed we wanted to work with. So that means when you use this formula, it only works if your angle is in radians. Okay? Just like that other proportion would only work if your units were in feet or inches. All right, so formula has 3 variables in it. They'll always give you 2 out of the 3, and your goal is to find the one that they don't give you. Okay, so for the first problem, I think I drew it, and did I draw it? No, I didn't draw it. I draw another one later on. Okay, so this one's just written out. So we've got a circle. Inside the circle, we have an angle of pi over 3 radians. And the radius of the circle is 4 inches. Find the length of the arc. Okay, so if you want kind of a visual of what's going on. Okay, we've got an angle of pi over 3. That's 60 degrees. So that would look about like this. Pi over 3. The radius of that circle is 4 inches. They want us to find the length of this segment in red. That's what you're finding. All right, so first thing that you need is the formula. Okay, if you don't have S equals R theta, you're going to be kind of stuck. So we start with that, and we're going to fill in everything that we can from what they gave us. All right, let's start with S. Did they give us S? No, that's the whole question. Find the length of the arc. So if they didn't give us that one, then they have to give us everything else. What did they give us for the radius?
Pi over 3. I mean, 4 inches. Sorry.
4, yeah. So the radius is 4. And what did they give us for theta, which is the angle? Pi over 3. Okay. 4 is not a fraction, but if you want to make it one, you could. What number could you put in the bottom? 1. And then you just multiply straight across. What do you get when you multiply those two together?
4 pi over 3.
4 pi over 3. Now that was a problem about finding arc length, so it needs a label on it. Okay, we just found the length of that arc in red. So what unit should we put on this that measures length, specifically in this problem?
Inches.
Inches, yes. Okay, when you're solving for S, you need to put a label on it, like inches or feet, whatever they give you. When you're solving for R, you need the same kind of label. When you're solving for theta, you don't, because theta is radians. We don't write RAD. Any questions on how we found the length of the arc there? Let's try this one. This time they give it to you as a diagram instead of writing it out. When they say find the length of the arc, they mean this. From there to there. Okay, what do you notice that's different, besides the fact it's a picture and not in words? The angle is in degrees. So if you use this the way it is, and you just plug into this formula right away, it's going to be wrong. Okay, so what's the first thing we need to do with that angle?
Convert it to radians.
Yep, I'm going to convert it to radians, so I'm just going to do that off to the side. And this is what we did on Tuesday. So how do we convert 130 degrees to radians?
Times pi divided by 180 degrees.
Yep, times pi divided by 180. That's both divisible by 10. And the degrees cancels. So when I convert 130 degrees, I'm left with 13 pi over 18. just leave it like that. That's what we'll fill in to our formula. Okay, so S we don't know. We're finding the length of the arc. What about the radius this time?
8 feet.
8 feet times. And JD, what's my angle?
13 pi over 18.
Yep. 13 pi. Doesn't matter if you just put the 13 over the 18 or the whole thing over 18. That's the same thing. All right. Anything there that we could reduce?
8 times 13.
Well, we can do that, but there is something you can reduce, so we can make that calculation easier. Anything there that the same number goes into both of them? Just like if you were reducing this. Forget about the pi. How would you reduce that?
4 goes into 8 and 18.
4 does go into 8, but 4 doesn't go into 18. 2, yep. 2 goes into both 8 and 18. So we can reduce by 2 and by 2. And we'll multiply it out. Generally, we're going to leave it as an exact answer with pi unless they tell us not to. What's 4 times 13 pi?
52.
Yep, 52
Pi.
pi. Over, the only thing left in the bottom is 9. And we do need a label on that because it represents length.
Feet.
This problem uses feet. Any question on that? Okay, so both of those we're finding S. Let's try one where now we're going to find the angle. Okay, so we have an arc length of pi over 4 centimeters, a radius of 12 centimeters. Find the angle. Well, one thing that would be important is these both have to be the same units. If they said one was centimeters and one was a different unit, everything has to be the same. Okay, I don't think I give you any problems where that would happen, but just to let you know. Okay, so start with our formula, and we'll start with S. Do they give me S?
Yes.
Yep. What do they give me for S this time?
Pi over 4.
Pi over 4. Yep. Okay. Do they give me R?
Yes.
Yeah, 12.
Yep. Radius is 12. Do they give me theta? No. So that's what I'm going to be solving for. Okay, so to get theta by itself, this problem has one step. What do we have to do on both sides to get theta alone? Yep, divide by 12. So we put a 12 there. Putting a times 12 in the bottom is the same as dividing by 12. So 12s cancel. And what do we get for an angle?
Pi over 48.
Pi over 48. Do we need a label on it?
Centimeters.
So did we just find a length?
No, we found 8.
We found an angle. We did not find a length. No, so we don't put a label on it because the label, when we're finding an angle, it's invisible. What is the label though that's not written, but we know it's there?
Radians.
Radians, yeah. That's pi over 48 radians. Now if they said, in the next part of the question, maybe they would say, take the angle and convert to degrees. So now if you had to, you could take that and change it to degrees. But in this question, they just said find the angle, so we'll leave it in radians. Any question on finding the angle? Okay. So let's finish up this formula with the one we haven't done yet, which is finding the radius. Okay, anybody tell me what they're thinking about how they would find the radius? Yeah.
You put a 13 on the S's and then the angle would probably with theta, and then you just divide 13 by 36.
So put 13 where the S is, and what about the R?
There is
We don't know the R. That's the whole question. And what did you say to plug in for theta?
36.
36.
Do I have to change
No,
it
you're gonna
first?
change the radius.
We have to change it first. Yeah. So if we plug in the 36 and divide by it, it will come out wrong. All right. So we're going to change 36 degrees to radians. And what did we multiply by to change it?
6. Sorry, pi.
Pi. And what do you divide by? 180. And you can check that, but 36 does go into 180 evenly. 36 times 5 is exactly 180. Okay, so your angle is pi over 5. All right. So now we have to solve for r. There's two things next to r that we don't want, the pi and the 5. And we can move both of them at the same time.
Just divide by pi over 5.
You could divide each side by pi over 5, or that's the same as what? Like what if it was a number like 13 equals r times 3 over 2? You could multiply each, or you could divide each side by 3 over 2. Or, what could you do instead of divide? Okay, so yeah, what did we say? Dividing, so we could divide each side by pi over 5, or multiply each side by 5 over pi. And that's easier, then we don't have to think about dividing by a fraction. Okay, when we multiply each side by 5 over pi, pi's cancel, the 5's cancel, and I think that's all that cancels. So the only thing we have to do now is multiply 5 times 13, 65. Okay, so that gives us 65 over pi. And remember, that's the radius, so we just found the length of something. What were the lengths measured in this problem? Feet. Yep. So if they asked you for the decimal, like how round to 2 decimal places, we just type in 65 divided by pi. Again, they didn't ask for that in this problem, but if they did, you'd say 20.69 feet. All right, so any question on using S equals r theta to solve for the S, the r, or the theta? So, last formula we're going to look at is for area. Okay, I'm going to start out by drawing 2 diagrams again, just like I did when we did arc length. You got that. I'm going to draw a 90-degree angle. And what I want to focus on this time is not the length of that arc. I want to focus on this area that is shaded in red. How much, in terms of the area of the entire circle, how much of the circle did I just shade in that picture? Yeah, a quarter. So the area is a quarter of the circle. Okay, now I'm going to double the size of the angle, and the goal is to look at what happens to the size of the area. If I double a 90-degree angle, I get how much? I get a 180. And if I shade in the sector, it doesn't quite look like a piece of pizza anymore because it's gotten too big, but it's still the same idea. Okay. How much of the circle is shaded in when you have an angle of 180 degrees? Half of it. So area is half the circle. So to get from 90 to 180, I doubled the size of the angle. What happened to the size of the area when I doubled the angle? It also doubled. Yep. So what that means is the size you make this angle and the size of the area are directly connected. If you make this angle half as big, you'd make the area half as big. If you triple the size of the angle, you would triple the size of the area. So they are directly, what was the word I used before? Proportional. Yep. And because they're directly proportional, we can solve this exactly the same way we did the arc length. We can set up a proportion. Okay. So let's start with the proportion. But remember, a proportion isn't useful unless you can fill in one side with actual numbers. So we'll figure that part out in a minute. Okay, so I've got a diagram. I have an angle and then an area that represents this kind of that wedge shape taken up by that angle, and then another angle and another area. Anyone think they could fill out the left side of my proportion using one of the four things that are circled? Theta over A? Sure. There's no really wrong way to do the left side as long as you set up the right side identical to the left. Now, what would go on the right side?
Theta 1 over A1.
Yeah, theta 1 over A1. Okay, so what we just did there would allow us to figure out, let's say that I told you the area for a 90 degree, let's say the area was 6 square feet. Well, if you know 90 degrees always gives you an area of 6. If you want to figure out the area for 180, that's how you do it. 90 always gives you 6, so 180 would give you 12. But the whole key is you got to know one side. So we got to go back to ours now and see if we can figure out that side and put in something on that side that's true. We can leave this side empty, and they'll give us information in the word problem to fill in on that side. All right, let's go back to our picture. So we've got a quarter circle, we've got a half circle. What if I drew a diagram like this? (360 degrees). How much of the circle would be shaded? The whole thing. So here's my initial side. Here's my terminal side. It's gone all the way around. And now the area isn't a quarter of a circle or half of a circle. The angle has gotten so big, it takes up the entire circle. So area is the entire circle. Well, if we can figure out that side of the proportion, 360 degrees, we have a number on the top, and the number in the bottom is the area of the entire circle, whatever that comes out to. All we need to do is figure out how you find the area of the entire circle. Does anybody remember what the formula is to find the area of a circle? Yep, pi r squared. So we want to do this, though, not in degrees. We want to do it in radians, because we did the other formula in radians, so to be consistent. What's 360 degrees in radians?
Pi over 2.
That's 90. 90 is pi. 2 pi. Yep, 2 pi, because pi is 180, so when you double pi, you get 360. So let's suppose that this angle was so big it took up the entire circle. That would mean the area would automatically be pi r squared. So there's our 1 foot equals 12 inches. If you have an angle that takes up the entire circle, the formula for the area is automatically pi r squared. Knowing that's true, we can figure out any other angle in the circle by just setting up a proportion. The left side, we don't know. That's what they give you in the word problem. And the right side, that's what we're going to figure out. So we have theta 1 is 2 pi. And that's not the only fact you could use, right? If you knew the area of a quarter circle off the top of your head, you could have used that. Just like here, you don't have to say 1 foot equals 12 inches. You could say 1/4 of a foot is 3 inches. That fact works too. It just usually, we go with what the simplest one is. And for us, 1 is the simplest number to use. And for area of a circle, most people know the area of a full circle. Not a half circle or a third circle or an eighth circle. They know the whole thing, pi r squared. Okay, so area 1 is pi r squared. Okay, what would happen on the right side? Yeah, the pi's would cancel out. So now when we cross multiply, we have 2a. Now our goal is to find a formula for a, not 2a, but for now it's okay. So we have double the area equals that part right there, r squared theta. How would we get a by itself so we get a formula for just the area and not double the area?
Divide by 2.
Yeah, divide by 2, or if you multiply each side by a half, that's just how our book does it. But taking half of something or dividing it by 2 is the same thing. And that's the formula for finding the area of a shape, like what's shaded in red right there. Those are sectors. This one is a whole circle, but you could still consider it a sector. Okay, so that's the area. Okay, R, what does that stand for? Radius, that's how big the circle is. And theta, that is your angle. And what unit do we have to use because of how we set up our proportion? We have to use radians, because right here we said 2 pi radians. We didn't say 360 degrees. It's not that you can't do these formulas in degrees. It's just that they look a little bit messier, because if I put 360 degrees in the top right here, think about what would not have canceled. I wouldn't have had a pi in the top. Because I did radians, I had a pi in the top and a pi in the bottom, and it's nice that the pi's canceled, so I don't have to think about it. That's why we did radians. Okay, any question on the formula? So, same idea, they'll always give you 2 out of 3 of the variables, and you have to solve for the third. They can give you a picture, or they can give you a problem in words. The first one is a picture. So find the area of the sector where you've got a circle radius 4 and an angle of pi over 6. That's that area shaded in purple right there. Now, is that shape that I just shaded in purple, is that a triangle? No, it's got 2 sides that are straight, but then it's got that third edge that's curved, just like a piece of pizza. So no, it's not a triangle. You can't use 1/2 base times height. That wouldn't work. Okay, so first step. What's the formula for the area of a sector?
Area equals half times 4 times pi over 6.
Can you just give it to me with the letters first, and then we'll fill it in?
Okay, r squared, and then what is that thing called?
Theta.
Theta?
Theta.
Okay,
Yep.
theta.
Theta. Yep. I say theta. But yeah, theta. All right. So now we'll fill in what was just said. What did you say the radius was?
4 squared.
4 squared. And the angle
Pi
is
over 6.
pi over 6. It's already in radians. I know that because it doesn't have a degree symbol. So pi over 6. 4 squared gives me how much?
16.
16. And then half of 16.
8.
So we get 8. And we still have times pi over 6. What number goes into both 8 and 6? 2. Okay, so our area is 4 pi over 3, but we have to put a label on it. So you have to remember how areas are written. They're written differently than lengths. And you have to look at the units that this problem used.
Centimeters squared.
Centimeters squared. Because area is two-dimensional, we need that exponent of 2. Okay. Any questions on that? Okay, so that's finding the area, and they gave you a picture. This is finding the radius, and they're giving you a picture again. Okay, what's different this time?
10 degrees on radius.
Yeah, it's in degrees, so first thing we should do right away is change that. Okay, when we change radians to degrees, 45 degrees is pi over 4. If you're not sure, multiply by pi over 180, and you will see that 45 goes into 180 4 times. 45 times 4. Okay, so that's not the answer, but that is the angle we need to use to get the answer. How about my formula? Can someone remind me what's that again?
Area equals 1/2 r squared theta.
1/2 r squared theta, and we'll go left to right, filling in what we can. Okay, do we know the area?
Yeah.
Yes. What's the area?
8 pi over 3 squared.
Right. Even if you weren't sure, like, wait, is that the length of the radius because it's written near that line? How do you know this number is an area?
Because it's squared.
Yeah, it's squared. It's inches squared. It can't be a length. So 8 pi over 3. Okay. Do they give us the radius?
No.
No, that's the question. Find the radius. And the angle, they give us pi over 4. Okay, so if you want to have all your numbers next to each other and not have that letter sandwiched in the middle, you can do that. You can, when you multiply things like 2 times 3, 3 times 2, the order doesn't matter. So this is easier for you to look at, then do it that way. Right, so let's simplify the right-hand side. What's half of pi over 4?
Pi over 2.
That's double.
Pi over 8.
Pi over 8, multiply straight across. 1 times pi, 2 times 4. So pi over 8. Now we've got a problem we had earlier. We've got a fraction in front of the variable, and we can get rid of both of these at the same time. What can we do on both sides that'll get rid of the pi over 8? Multiply by 8 over pi. I guess I can put it right here. Multiply by 8 over pi, 8 over pi. 8's are gone, pi's are gone. And what happens on the other side?
It turns into 16 pi. About 16 over 3, right? Because the pi's cancel.
Well, the pi's do cancel, yes. Pi's cancel. And what are we left with?
8 times 3.
8 times 8? 64. So 64 over 3. And is that my radius? That's my radius squared. So I still need my radius, not my radius squared. We're going to take the square root. So when you square root a fraction, you've got to do the top and the bottom separately, just like that. So that would cancel. What's the square root of 64? 8. That comes out nice. But does the square root of 3 come out nice? No. And unfortunately, that's kind of annoying because you can't leave the square root in the bottom of a fraction. So this isn't really trig anymore. This is now getting into arithmetic about leaving roots in the bottom. Does anybody remember how you fix having a root in the bottom, what you have to multiply by? So yeah, you're going to multiply the top and the bottom by the same thing. And what would you multiply by? Square root of 3. Yep. Well, what's the only thing you can multiply something by and it doesn't change it? 1. So you really got to multiply by 1 here. But we're writing it in a special way.
So square root of 3 over.
It has to be the square root of 3 over the square root of 3. And the reason why we do that is because what happens when you do the square root of 3 times the square root of 3? It cancels. That's the square root of 9 when you put those together. And what's the square root of 9? 3. Now at the top, you can't put them together. Like you can't write square root 24 because that's not a square root. That's just an 8. So all we can do is 8 square root of 3. And that is my radius, fully simplified. What should we put for a label on it? Inches. Because the radius is a measure of length, and inches was what they used in this one. Okay. Any questions on that one? Yeah.
Are there going to be problems where we're going to do all that squaring stuff on the test, or?
Yeah, you could end up with a problem where you have a square root in the bottom. Yeah, and if it's a multiple choice question, you somehow have to know that this is the same as that, or if it's a short answer, you'd have to figure this out yourself. So if you had something like, let's say like 5 over the square root of 6, what would you multiply the top and bottom by to fix that? You multiply by the square root of 6. And what would you get in the bottom? 6, because that's the square root of 6 times square root of 6. That's square root of 36. So that's 6. And then in the top, you can't put those together. You just leave it like that. So that's how you simplify a square root in the bottom. Okay, so that's solving for R. So we did that. We solved for A. Let's try the last version where we solve for S. I mean theta. Solve. Okay, no diagram this time. They just tell you the area, they tell you the radius, and they put a question mark, which means they don't know theta, and they want you to find it. All right, so one more time, can somebody else that hasn't told me yet, what's my formula for area? Yep.
Area is equal to 1/2 radius squared times theta.
And as long as you're not solving for R, you're never going to have to worry about that square root stuff. Okay? So this is the only kind of problem where that could happen. They tell you R this time. So that square root thing's it's not going to be an issue. All right. Do they give us the area?
Yeah.
Yep. What is it? R over 2. Do they give us the radius?
Yeah.
Okay. What's that?
3 squared.
3 squared. And do they give us theta?
No.
No. So pi over 2 equals 1/2 3 squared theta. Okay. Now, let's do this out on the right-hand side. What's 3 squared?
9.
9. And then I'm just going to write half of 9. as 9 over 2. Right, rather than 4.5. I'm just going to leave it as 9 over 2. And what would we multiply each side by to get theta by itself?
2 over 9.
2 over 9. So 2's are going to cancel, 9's are going to cancel, and the 2's cancel there. So we're left with pi over 9, and what did we just solve for? Theta, which is, when theta represents what? An angle. You don't need a label then. The label is implied. We don't write it. It's pi over 9 radians. Only time you have to write a label on an angle is if you want it in degrees, but this formula doesn't give you one in degrees. You would have to convert that by hand if you need degrees. Okay. Any question on that? Okay. So in the homework, there's a couple word problems about arc length and area, and one of them is going to involve a clock, and they tell you that like the minute hand is at 12, and then it's going to 3, and they ask you how far the tip of the minute hand moves from there to there. So in this case, the path that the tip of the minute hand travels is really what shape?
The arc.
It's an arc, yeah. The path that the tip is traveling is an arc, and then this happens to be a 90-degree angle. That's easy to figure out because it's perfectly vertical and perfectly horizontal. But what if the minute hand went from 12 to 4? How would you figure out the size of that angle?
We need to know the arc length and radius.
We wouldn't need to know that on a clock because everything's equally spaced. So we can figure out the angle on a clock without knowing the size of the radius or the angle, or the arc length. So how much does the minute hand move every 5, or the hour hand, or however you want to think of it, every number? Every number it moves 30 degrees. Because to get from 12 to 3, that's a 90. So it must be 30, 30, 30. So 12 to 4 would be how many degrees? This would be 120. 30, 30, 30, 30. And then if you go another 30, you're at 150. And another 30, you're at 180. So you can figure out the angle. And they don't give you one that's in between an hour. They always say it's like on the 12 or the 2. They don't give you like in between. So it's always going to be a multiple of 30. And the length of the minute hand is like your what?
Your radius.
That's your radius, yeah. So that's the length of the minute hand is your radius. And then you can figure out the angle because everything is equally spaced. And then you use the formula to find the arc. Another problem they give you is a pendulum, okay, swinging back and forth. As a pendulum swings back and forth, what's the shape that the pendulum makes? Yeah, it's an arc. Okay. And the length of the string or the rod or whatever's holding the pendulum, that's like your what?
Radius.
That's your radius, yeah, because it's pivoting from this point right here. So if they ask you how far does a pendulum that's 2 feet long swing, if the angle is like 30 degrees, well, you've got your angle. They'll tell you how long the support is for the pendulum, and then you plug it into the formula and you can find the length of the arc. So there's a couple problems like that, but it's really just arc length problems. All right, so those are the homework questions for tonight, 71 to 87 odd and 91 to 94 all. And tomorrow we've got the test on 1.1, 2.1 part 1, and part 2. Okay, topics that'll be on there from 1.1, we did distance and midpoint formulas. In 2.1, we talked about converting between radians and degrees. Both ways, radians to degrees, degrees to radians. And in the second part of 2.1, we did arc length and area of a sector. And that's everything that should be on the test. You can have a reference sheet if you need it, like any of the formulas. We did a few formulas: distance, midpoint, arc length, and area. So there's 4. And then there's 2 conversions: degrees to radians, radians to degrees. So you might want those conversions as well. And I will be after school today. If anybody needs to come by, if you have to make anything up or see me for extra,